In this video, we first study the definition of a vector space, which is a set with addition and scalar multiplication that satisfy a set of axioms, followed by proving some properties of vector spaces. And finally, I'll give a few examples of vector spaces. Okay, let's start. So here's the definition of a vector space. Let V be a set. So this V will be the vector space, and F a field. If you don't know what a field is, it's just a set with usual arithmetic operations like addition, subtraction, multiplication, and division. So you may consider this as the set of real numbers or the set of complex numbers, for example. Then V is called a vector space over F, over the field F, if it is endowed with addition and scalar multiplication. Now, those are the basic operations of vector space with the following properties. So here's the set of axioms of those operations, addition and scalar multiplication. If U and V are elements of the set V, then U plus V is also an element of the set V. So this means this set V is closed under addition. So if you pick two elements from V and adding them, that will not go outside of the set V. It stays within the set V. Next, if U, V, and W are elements of V, then we have this associativity. So adding U and V first, then to that add W, that is equal to first add U and W, V and W, then add it to U. So they give the same results. And third, commutativity of addition. So for any elements U and V, U plus V is equal to V plus U. So we can always swap the order of addition. And fourth, the existence of additive identity, which is called zero vector. So for any element V in the set V, there exists an element called 0 in the set V that satisfies this. So V plus 0 is equal to 0 plus V is equal to V. So adding 0 element or 0 vector to some vector V doesn't change the vector V. And next, the existence of additive inverse for each element of V. For any element V in the set V, there exists another element W in the set V such that V plus W is equal to the 0 element. So the 0 element is defined here. So this W is called the additive inverse of V. We will see later that such a W is unique for a given V. So far we have been explaining the axiom satisfied by the addition operator. And next, scalar multiplication. So scalar is an element of the field F. So let A be an element of F and V be an element of the set V. Then we define A times V, which should stay within the set V. So we say this the vector space V is closed under scalar multiplication. So it scales. So the vector V is scaled by the scalar F A. And next, associativity of scalar multiplication. So let A be elements of the field F and V be an element of V. Then first multiply B, V, then multiply by A. This should be equal to first multiply A and B. So this A times B is the operation within the field F. Okay. Then we multiply that product to the vector V, and they give the same result. So here, two kinds of multiplication appear here. So this b times v is scalar multiplication between a field element b and a vector element v. And this one, a times b, is multiplication between two elements of the field f. Next, distributive law. So for any elements a, b of the field f and any element v in the set v, then a plus b multiplied to v is equal to av plus bv. So here again, we are actually dealing with two kinds of additions. Okay, this addition here, a plus b, is the addition within the field f. And this addition here is the addition between two elements of the vector space. And next is another distributive law. For any element a in the field f and any elements u and v in the set v, a times u plus v is equal to au plus av. Again, in this case, this addition and this addition are both the addition in the vector space. And finally, the identity element of scalar multiplication is just the identity of the field f. So for any vector v in the set v, 1 times v is equal to v itself. So this 1 is the multiplicative identity in the field f. So if we multiply this constant to any vector, doesn't change that vector. So any set with addition and multiplication, scalar multiplication, satisfying all these 10 axioms is called a vector space. Now, let's prove some basic properties of vector spaces in general. Let V be a vector space over a field F. So it's a very general vector space. Then the zero vector, the additive identity, is unique. So there are no two or more distinct zero vectors in a given vector space. There's only one zero vector. And two, for a given vector v, its additive inverse is unique. So if one element in the vector space v is given, then its additive inverse is unique. That means there are no two distinct inverses for a given vector. Therefore, we can denote its additive inverse as negative v. And next, for any element v in the vector space v, 0 times v is equal to the zero vector. Here, this 0 is the zero element in the field f. Okay, field is a set with addition and subtraction and multiplication and division, and it has the zero element. So in the case of the set of real numbers, it's the number 0, right? So 0 times any vector is the zero vector. And next, for any field element A, then A times the zero vector is equal to the zero vector. And finally, for any field element A and any vector space element V, negative A times V is equal to negative of AV. So this means this negative A is the additive inverse of this A in the field F. Okay? And this negative AV means the additive inverse of this vector in the vector space. Okay? So because this holds, we can just write either this or this as just negative AV. So it doesn't matter where we put the parentheses. Okay, so let's prove each of them. The first one is easy. Suppose we have two zero vectors, 0 and 0 prime. Okay? Then 0 prime is equal to 0 prime plus 0 because this 0 is the 0 element. So adding that doesn't change this 0 prime. But here, 0 prime is also assumed to be the 0 vector. So adding this to this 0 doesn't change this 0. So therefore, this is equal to this. Therefore, if there are two zero elements, these two elements must be equal to each other. And next is the uniqueness of additive inverses. So for a given element V, let W and W prime be the additive inverse of this element. Then we should have V plus W is equal to the zero vector and V plus W prime is equal to the zero vector. So we have this. W prime is equal to W prime plus 0 because adding 0 doesn't change W prime. But this 0 is equal to V plus W because this W is the additive inverse of V. So adding them together gives 0 vector. And then by the associativity of addition, we can change the places of these parentheses. So now we have this. And next, by the commutativity of addition, we can swap the order of addition. But this W prime is an additive inverse of V. So V plus W prime is equal to the zero vector. But adding the zero vector to W doesn't change the W. Therefore, W prime is equal to W. And next, multiplying the scalar 0 to any vector gives the 0 vector. To prove that, we first know that 0 is equal to 0 plus 0 in this field, right? So 0 times any vector v is equal to 0 plus 0 times the vector v. By the distributive law, we have 0v plus 0v. So from both sides, we can subtract or add the the additive inverse of 0v. So that is this one. So if we add them, then this left-hand side becomes the 0 vector because we're adding the additive inverse. And from here, one of this or this becomes the 0 vector because this plus the additive inverse of this is 0 vector. So we have this on the right-hand side, but adding 0 vector to any vector doesn't change that vector. Therefore, 0 times v is equal to the 0 vector. And next, multiplying any scalar to the 0 vector gives 0 vector. To prove that, we expand like this. So a times 0 vector is equal to a times 0 vector plus 0 vector. Because 0 vector is a 0 vector, so adding that to the 0 vector doesn't change the 0 vector, right? Then, by the distributive law, we can expand like this. So a is times 0 vector plus a times 0 vector. Now, adding to both sides the additive inverse of this thing, a times 0 vector, this one, then the left-hand side becomes the 0 vector, and the right-hand side, on the right-hand side, this remains, one of this remains. So we have a times 0 vector is equal to the 0 vector. And finally, let's add these things together. So a times v, where a is any scalar and v is any vector. And negative a is the additive inverse of this a in the field F. And times v, the same v here. By the distributive law, this is equal to a plus negative a, whole thing, times v. But this is 0 in the field F. But 0 times any vector gives the 0 vector. What this means is that this thing here, negative a times v, is the additive inverse of av. Therefore, we have this. So additive inverse of AV is equal to negative A times V. Now let's turn to some examples of vector spaces. The first example is this. Let F be a field, which is typically the set of real numbers or the set of complex numbers. And let us denote by F to the power of n be the set of all column vectors with n elements. So each of these elements is an element of the field F. So this is a column vector, and we consider the set of all column vectors like this one. Then this space is a vector space with the usual vector addition and scalar multiplication. So for example, so if we have these two column vectors, so we know this transpose sign. So if we add them, this addition is defined by this, which is again an element of this vector space. And for any element A in F, the field F, and any column vector in F to the power of n, if we multiply A times V, multiply A and V, then we have this is equal to this. So this is the definition of scalar multiplication for column vectors or matrices, which is again an element of Fn. So this space Fn is closed under addition and scalar multiplication, and you can check all other axioms are satisfied. So this is a vector space. Next example is the set of sequences. So let F to the power of n. Note this n. No, this n is the set of all natural numbers. So, and this denotes a sequence of numbers or any field elements. Then we can define addition between two sequences. So let A denote one sequence and B denote another sequence. We can define the addition between these two sequences by this. So sequence A plus sequence B is defined to be the sequence of all elements, sequence elements added together. And scalar multiplication is defined similarly. So let C be any field element and CA, so C a constant and A a sequence. So this is a new sequence defined by this thing. So in this way, we can define addition and scalar multiplication, and you can show that these operations satisfy all the axioms of the vector space. And the final example of this video is the set of real valued functions on the real numbers. So that means, let's say f of r, this r is the set of real numbers, is the set of all functions from real numbers to real numbers. Okay, then we can define the addition between two functions by this. So this f plus g on the left-hand side is a new function, which is defined by this. So at each x, which is a real number, we define the value of f plus g as this. So the value of f at x plus the value of g at x. So in this way, we can define a new function here. And so this gives the addition between two functions. And for scalar multiplication, let C be any real numbers and f be any function. Then this new function cf of x is defined by the constant c times the value of the function f at x. So we define the value of this function at each point in this way. So we have defined addition and scalar multiplication, and you can show that these operations satisfy all the axioms of the vector space again. For example, the additive inverse of a function f, so we denote that by this, negative f is defined by this. So negative f, this is a new function, which is defined by f times -1. So f of x is given function. And you should check all the other axioms are also satisfied. Okay, so that's all for this video. See you later. Bye. Thanks for watching. If you like this video, please hit the like button and subscribe to this channel. See you next time. Bye.